I've taken over the years is really the perspective of the devices themselves, of trying to understand what can you do in an environment where the different devices are disconnected. And we're looking at a lot of different environments here. I'll bring them all up. I don't have my clicker today for some reason. We're looking at everything from mobile vehicular networks, where I'm going to talk a little bit about the large-scale sensor networks that we anticipate for vehicular networks, to mobile social networks where people are walking around with mobile devices and trying to communicate with the other people in their environment, not necessarily through the infrastructure, but directly to each other, to disaster recovery networks where there obviously is no infrastructure and you have to deal with the environment where the infrastructure has been destroyed, to things like animal sensing networks, where we need to have small devices that are going to see lots of different mobility patterns and lots of different connectivity issues. And I will, put up the question that I'm sure all of you have seen. Isn't the infrastructure enough? Don't we just need our handheld devices with 3G, 4G, Wi-Fi, whatever it might be? Why would we ever need the devices to talk to each other? And in my mind, there's lots of limitations, and any one of these is enough to break the assumption that the infrastructure is enough, but any of these could actually happen. We can deal with the fact that it might be unavailable, whether it's gone down due to some disaster, or it's just gone down due to a blackout, or it might not be available. I'm going to show you some pictures of the Wi-Fi coverage on our campus, and it's actually not very good once you step outside of the building. It could be overloaded. Well, my students found this great graph. We're looking at capacity. We're sitting about here, and so people are saying, capacity is good enough. We really still have some space, but the demand is increasing immensely, and the predictions are that the demand is going to be exponential. And I agree with them. And while the capacity is increasing, I don't think that the capacity can increase with the demand. Maybe that's not the perfect graph. They're not, predicting quite right. But the more that you give people, the more that they want. Okay? In a lot of cases, people just think it's too expensive to use. There are a lot of people who just don't want to pay. They want to be able to communicate amongst each other without having to pay the overhead of dealing with the carrier. On top of the fact that they're now adding caps on usage to almost all of the data plans that I've heard have caps on usage. They're kind of hidden sometimes, but if I have a cap on my usage, there's no way I'm going to let somebody else use that much of my data in any kind of cooperative sense. So it actually stifles any large-scale cooperative solutions. So what I want to do amongst all of these different domains, I'm going to talk about a couple solutions in a couple of different domains, is just enable communication among the mobile devices that doesn't depend on the infrastructure support. That doesn't mean it doesn't use it when it's available, but what happens when it's not available? Can we use it what can we do when it's not available? So I kind of look at this as, embracing disconnectivity. So much has gone on of people looking at environments that were disconnected that, there's this whole class of network solutions called disruption, delay, tolerant networks, interconnected networks, whatever you might be. So the D that I like to focus on is the disconnectivity issue of trying to deal with that. And people looked at managing disconnections in lots of different ways. And 5-10 years ago, ad hoc networking was really popular. And people came up with some really interesting solutions, some challenges to dynamic networks. But the assumptions in those networks was that disconnectivity was a failure. And that if I didn't have a connection to the node that I was trying to talk to, I had to find some workaround. So this meant that the scale was limited, the applicability to different environments. This didn't work in any kind of clustered environment. So it kind of died down that this is a very specific solution that didn't work in different environments. So what do we turn around and say? We expect disconnections. And this is really the philosophy that delay tolerant networking has taken, that we want to cooperate to overcome these disconnections, which enables much larger scale solutions and application to more natural behavior. But if then we try to say we want to embrace disconnections. It actually, if we look at how we have, what kind of solutions we want to provide for these environments, we need to come up with some new protocols and architectures. Because the problem is if we try to push this mobile interconnected networks into the protocol architectures that exist already, we have a lot of problems. And one of the biggest ones is that some of the things that are everyday and common in a disrupted or an interconnected network, intermittently connected network, are considered out of band for the traditional protocol stuff. Things like discovery. If I want to find all of you and find it in my neighborhood, there's this assumption in the internet stack that I'm going to plump down, I'm going to find everybody, and then I'm going to go about my business. And that's not going to change that much. It may change every once in a while, but it won't change that much. So it's kind of done out of band. The same thing with configurations. I mean, if we assume that the configurations are not going to change that much, we can do configurability out of band. But when things are changing so much, we can't take those things out of band. So I've been just thinking about what are the components. And so I kind of came up with these 3 classes of things that we have to do. I think you may or may not agree with how I broke this down, but it kind of captures what's going on in these networks. And if we look at from maybe the bottom up, I'm not trying to build a new stack, I'm just trying to find out the components that we need. Everything is built on top of contacts. Who can I reach? How can I find them? Who is one hop away from me? Because those are the people that I can, nodes, I say nodes people, whatever, that I can directly communicate. And this is going to enable any kind of communication. This is the main building block. This is kind of the links, but they're not there all the time. They're changing all the time. And so we have to understand how to find those contacts. And then we step up and say, okay, now that I know who is maybe around me, I want to look at who's directly near me. I want to look at what's around me. What's in my neighborhood? Who's in my neighborhood? What services are available here? What data is available here? What's going on? Is there congestion or no congestion? And that is what's going to enable a lot of the optimizations that let the solutions for delay tolerant networking scale to larger networks. And finally, it's the content. These are obviously content-driven scenarios. The applications are going to drive what we need to do in these scenarios. And in a sense, we've swung in our research to a point where if we don't have a good application driving what we're doing, nobody's going to care about what we do. And it's very true in this environment that I could come up with 80 million different solutions for solving things in delay tolerant networks. If I don't have a good application that needs it, nobody's going to care. So we need to focus on understanding not specific applications, but understanding the class of applications that people might be using in these environments and how they access and use their data, because I truly believe that it's going to be different than your traditional internet data access. You know, I'm not going to say I need to send a message to Sam through the DTM. I'm probably going to look for a service, or I'm going to look for a data, some type of data, or maybe I'm going to look for a group of people, any number of different things. So just to give you a little more detail about what we have, and we have what I'm talking about in some of the projects that we're doing in this area. So when I'm talking about context, I really mean, so when I came up with this classification of contacts, context, and content, I had voice. So if you are having a hard time telling the difference, I apologize. Context realize who is near me, and how can I find them. And the biggest challenge in this environment is really that if I don't find anybody, I'm not going to be able to do anything. Contacts, the opportunistic communication enables the opportunistic communication depends on the contacts. And the contacts enable the communication. How many people I meet, how many nodes I meet, how long I'm going to have some communication with them is going to determine what I can actually do in a different environment. But these encounters are very unplanned. We can't do some, regular checking. Okay, every hour I'm going to check to see who's near me. That's not going to suffice in finding anybody. And the nodes are very energy constrained. So I have to be very careful about how I do any type of discovery in these environments. And on top of that, the nodes have lots of different interfaces. And each interface may have different channels. So I can't, unless we pick one control channel and one interface for everybody to look for each other, I'm going to have to coordinate communication across these different channels, across the different devices. So In this domain, so far we've focused mostly on discovery. And we have two projects. One is looking at energy efficient asynchronous data discovery. This is something that you could use in a sensor network or in a social network. And it's just trying to do better discovery of the nodes in your neighborhood given energy constraints. But the second one kind of builds on that. And I'm going to, if I have some time at the end, I'm going to talk about this particular one. It's called Sequest. And it's multi-interface collaborative discovery. So if we actually let the nodes collaborate on how they define each other across multiple interfaces, we can save a significant amount of energy and actually find more devices. The second thing I said was context. What's going on around me? Who's near me? So by this, I'm looking at how can I optimize the solutions I'm dealing with. I want to know information about who are my neighbors, who is in my neighborhood, who else is in my larger neighborhood, what's going on in my neighborhood. And these are going to help me find solutions. So if I'm so focused on only providing a pure delay-tolerant networking solution, right? If I'm trying to send a message from this guy to this guy, I'm not going to be able to take advantage of the fact that there's connectivity already. So knowing that that node is my neighborhood, I might be able to do something better. What's going on in my neighborhood? Is it congested? Is there a lot of data that might be out there that I need? What services are there? Are there the people that I'm looking for? A subset of the people I'm looking for, any of these things. And the biggest challenge here is that mobility creates the high churn. So anytime I try to find out information about my neighborhood, it's going to change very quickly. So the solutions that we provide, that you use in this environment, have to be opportunistic on top of all the other opportunistic things that are going on, so that I can't rely on information about my neighborhood, but I want to take advantage of information about my neighborhood. It's kind of this think global, act local type of approach that says, okay, I want to solve the problems of the whole network, but let me see what I can do in my small part of the network to make things better for me and everybody else. If I look at the types of projects that we're doing in this area, they're mostly routing projects. The cache-based routing is actually Sam's work. I'm not going to talk about that. If you have any questions, you can ask him. Mercury is this cluster-based routing approach that I was talking about. How do we enable communication amongst inside a cluster, but also between clusters? We have a localized congestion management protocol. That is actually what I'm going to try to talk about today. And then we have a membership management protocol also. So I'm going to leave those to let him answer your question about those, but you have some questions for us about. That's what happened. I was trying to figure out what I wanted to talk about. I'm like, I can't talk about sales because he's here and you can ask him yourself. And the final piece really is the content. How do I deal with data in these environments? And what I believe is truly is that the biggest challenge is that I'm not, communication right now is very user-centric, or service in that maybe a web service or some particular data I'm looking for. But I think communication on these large-scale networks is going to be group-based or service-based or content-based or location-based. And we're not going to have one solution that solves problems for all of these, but maybe we can come up with some solutions that satisfy classes of applications that manage data in these ways. And here, essentially, the challenge is that the specific services and applications are very application-dependent. So again, we have to figure out what these classes of applications are so we can help them. So I'm going to now reverse the order and talk a little bit. Oh, sorry. And there's a couple projects that we've looked at in this area. The one I'm going to talk about today is Locust, which is a location-based vehicular sensor network. I put some group-based communication, both Anycast and Maycast, in this domain because I believe those are enabling different types of data deployment or data access in these networks. So Anycast, where we've enabled group-based communication, and Manycast, where we're looking at trying to understand the space between unicast all the way up to multicast and what that means in a delay-tolerant network. Again, actually, these two pieces of work are sandwiched. To give you credit. Why did you guys take him? I need him. I can come back and do work with him. Okay. I'm going to start at the top, though, because like I said, all of this means, all of this work all of these networks are driven by the applications and data that are in them. So mobile applications are all about their data. User data, the sensor data, the location, whether it's location-specific data, whatever it might be. And the example that I like to use, because that's the project I'm going to talk about in a minute, is a large-scale vehicular sensing. Okay? What we'd really like to be able to do is put sensors in cars. This is really technically possible. There's nothing stopping from doing it. It's actually economically very difficult if I wanted to put sensors in all the cars and communicate. And logistically very challenging. What's happening is we now think about this, but cars are an untapped resource. Right? I mean, think about the ParkNet project that's going on here. You're using the cars to go run around and find information for it. Okay? But on top of that, beyond the resource of finding data, cars are also a resource in that they can provide networking services, storage services. They're large scale. So, I mean, think about all these cars. They're large scale, they have geographic coverage, they have diverse mobility patterns, and they have a lot of resources, both energy and storage. Okay? And what this gives us, if we add the sensors, both environmental, traffic, local conditions, parking spaces, whatever it might be, we end up with a very large scale distributed sensor network. Okay? If we take this network and we try to throw it into a domain that only has 3G, 4G coverage, you're going to saturate the network very quickly, especially if you add anything like images into the picture. Maybe all you're doing is temperature readings or speed readings. You might be able to do something. But if you have this density of coverage, I didn't write the numbers down. If you have this density of coverage, and even just 10% of the cars in Chicago are trying to do something, you maybe get 5 kilobits per second if you're lucky. And if there's even more, but I think it was 1%, you get 5 kilobits per second. If you get 10%, you're getting 0.5 kilobits per second. You're getting on very, very low data rates. But if we try to add any interesting data to this, you're going to swamp and overwhelm the network. Certainly, you can wait until the evening and let the cars come home, park in their garage, upload the data. But that does not give you the online, live access to the data that we'd like to be able to enable. Okay. So what we are doing is we're actually deploying a testbed in Illinois, which does not look like that. Maybe we have 3 or 4 cars on the road at once. Yeah, that's Chicago. That's not Champaign. But we've talked to the people on campus, the campus and facilities people, and they've allowed us to put, right now to start with, 100 nodes, 100 devices, and 100 cars. And these cars will allow us to set up a large test bed. And the interesting thing about it is that it's very contained. It's within the campus. I'll get there in a second. So our goal is live data sampling. And believe it or not, energy efficient node discovery. Didn't I just say that cars have abundant energy? Well, it turns out that cars have abundant energy when they're running. If you turn the battery off and the car stop running, and you leave the onboard diagnostics or the GPS or the Bluetooth on your car battery, your battery's going to die. So maybe I don't have to be quite as careful as the energy that I'm using on my phone, but it is no longer abundant if a car is parked. And since we have no control over where these cars are going and when they're running or when they're not running, we have to be very careful about how we use the energy. So we have to design solutions that when they're running, try to use as much resources as they can and don't need to be energy efficient. But when they're not running and they're still participating in the network, they have to be energy efficient. So the benefits of doing this, for somebody asking, well, why did you want to do this? This is, Champaign, Illinois is not a dense network. It's not a dense city. Why would you ever need this? But it really gives us a great opportunity to test out new things. Since we're putting in the facilities cars, we have uncontrolled mobility. We don't know where these cars are going. We don't know when they're turning on and off. Very unpredictable node density. Although it is predictable in the evening because they probably all go park in the parking lot together. But this gives us the ability to test new protocols and services against these very unpredictable conditions. And the fact that they are all facilities cars is that means they're all on campus. So they'll all stay within the campus domain, which gives us a nice density as compared to if they were all the students' cars, and they were going random places in the evenings, and they weren't doing anything on the weekends or any of this. So we actually really do expect relatively high car-to-car contact frequency, and which allows us to do some leveraging the clustering when we're trying to solve our create our solutions.
Unless we find out people are using the cars in ways no one knows.
If people are using the cars the way that nobody knows, the guy in facility services is going to say thank you, you're fired. It was very interesting. So people have asked us, well, we cannot stop the people using the cars from turning them off. Okay, so we do need access to them to go turn them back on again when they've turned them off. But the manager of the facilities and services has said, they're my cars. I can do anything I want with them. My employees will have to just deal with it. We're not taking pictures of the employees. We're just monitoring their location, and we're monitoring the cars. So they may not be thrilled with it, but I think they've already started deploying some GPS, just straight GPS on the cars already to keep track of where they are. So we're not really doing that much more Big Brother watching than what the facility and services was already doing. And so why facilities and services was interested in this is one of the projects that I'm associated with is this project called Green GPS, where they're trying to enable more fuel-efficient routes. So the facilities and services are very interested in finding more fuel-efficient routes. And so this test bed will run some applications on top of it that'll let the facility service people get some.
Are you going to run applications that require car-to-car communication?
Yes, we will. The Green GPS may or may not. They want live data. Anything that wants live data, I'll show you in a second. Anything that wants relatively live data is going to have to do car-to-car because the coverage is not universal on campus. And I'll show you in a second what it looks like for our just initial tests. Okay, so the basic idea is the cars run around, they run their experiments, they generate some output, and they're going to upload it to a local server. Now I said, oh God, why do I want to do that? But we actually need to collect the data to figure out what's going on. So when we do have connectivity, we upload the data to a central service. So each car is looking for APs and actually looking for other cars to connect to. They'll send their data to other cars. So if you have a car that's parked in a parking lot that has no connectivity, you'll never get that data unless somebody opportunistically comes by and gets it from them. Data gets sent to the server, and the server displays the whole thing. I actually have an undergrad student working almost all summer trying to get this, beginning of the summer, getting this interface set up, but it works really nice. I'll show you a couple of snapshots of this. So, I know your hardware person is not here, but you might be interested in what hardware we're using. We're using a mini PC, either a geode or an atom board. And somebody's asked us a couple times why we're not using a more powerful board. The thing is that these cost, if I remember correctly, these cost about $250. And if we want to deploy 100 to 200 of these, we can't jump up to the more expensive $1,000 boards that give us more processing power. So we're limited. So given that we want this large deployment, we have to deal with the constraints that it's going to give us, and it is pretty constrained. Our storage is compact flash, which is slow, so we have to be careful about that. Memory is not very high. I forget. I think it's. I'm blanking on this right now, but it's not a large amount of memory. The networking we've set up so far, at least I'll put that there because I'm still trying to figure out how to get that to work on our cars. 802.11 AGN, and we can put ZigBee on it if we want to, and WiMAX on it, and we're actually talking to Ray here to try to figure out how to get WiMAX and set up in here. The reason that we're using, right now there's two radios in the current prototype has a G and an N radio. And the N radio is really important because out on the streets, the G radio gets almost no connectivity. So we actually have to have the higher coverage to be able to get anything out on the streets of campus.
We had out on the G gets no
almost no signal on the
streets.
streets.
Because of Doppler?
No, it's because the base stations are in the buildings.
So it's just the
N is
strength.
it's
even
just
if you're standing still.
It's pure signal strength issue. You can step outside of most of the buildings. We did a test where we ran the cars with G and with N, but I don't have that. I don't have the data for the G test. I'm going to make them do it here so I can tell you what the difference is. And on top of that, somebody originally said, well, why don't you just put phones in the cars and just let the phone be your platform? And I thought that would be wonderful. If you put a phone in your car, it's even worse than a laptop with a G because the antenna is even worse, and you're going to get almost no connectivity out of the cars on the streets, unfortunately. Connect to the battery when the car is running, but we have a backup battery when the car is not running, so we have to manage that well.
Are you using any special antenna?
For the radios? Yeah, I tried to get my students to send me a picture of it, and I don't know why they didn't. We have a box with antennas that are about this big, so the N has 3 antennas, and the G has 2 antennas just because it has 2. The board that we have has 2 antennas on it.
The box would be inside the car.
The box, so the plan is for the antennas to sit in the back window of the car, and for the box to be in the trunk, or depending where it is, because we'd like the GPS to be as close to a window as possible. We'd like the antennas to be as close to windows as possible.
Have you secured the box?
We haven't. It's not clear why anybody would want to steal one of these boxes.
No, I mean, accident.
Oh, for an accident, we have to figure out how to do that. We're still working on the prototype of getting everything to work, because we were actually having some problems with the antennas interfering with each other. They put them too close together on the first prototype. The N and the G antennas were interfering. So yeah, there is some engineering going on to make things work correctly. They sent the cars out and they weren't getting any signal or they weren't getting connectivity. They were seeing the signals because of the interference. The people at UCLA used really nice looking boxes, and they had to put them in plexiglass so that they wouldn't get stolen. We've also, so along with the green GPS application, they want to put a phone on here too, because they want the application to run on the phone. They're going to have to lock that thing down, because that will lock. I doubt this stuff will. People won't know what it is, but we are going to have to be careful because things will get jostled around. I mean, these are facilities cars. They're going to be throwing stuff in the trunk. So we do have to be careful about where we put everything. The best thing we could do is if we could put it under the seat, and then put the seat back down. That would be great. But we do have to be careful that it doesn't overheat too. So we have GPS and we have Bluetooth. Bluetooth goes to, right now, the main sensors, data that we're dealing with is location and information about the engine. So the OBD2, onboard diagnostic, OBD-II, and interface to a smartphone. So that's the technology that we have right now. And I think, if minus the phone, all of it together runs about $350 or something like that. So we're trying to keep this price down as much as we can. If we bought a lot more, we might be able to bring it down a little bit more for bulk, but I think our bulk business is still quite enough to hit any bulk rates. Okay, so what data do we have? This is in the infancy of this deployment. So the first thing that we did, just to make sure everything was working, was we ran around and we wanted to find out what the signal strength was, what the uplink and downlink throughput was, and just some basic, what the ESIDs were, and AP information. So the first thing we did was signal strength. So this was a bunch of cars running around and collecting signal strength information on the campus. The red is good signal strength. And that's our building right there where those cars are parked. The gray is no AP at all. And I'm pretty sure this light brown is, they saw an AP, but they couldn't get any connectivity. They couldn't do anything. So there's a lot of parts of campus that, this is the main part of campus, but there are campus buildings all around this area that we show. So there's a lot of parts that, if a car parks, has to go do some work over here and parks over here, it's going to have no connectivity. And this is with N. This is not with G. So even with N, we're getting decent connectivity.
And this is not with you planning to install a few extra
We could.
lights in the building, some strategic location.
I'm not planning on putting out anything more than what the university has there. We could show this to them and say, look, you have no coverage. But my plan was to work within the constraints of what the university has. I mean, if they're interested, I can show them. But I'm not sure how much they care about covering the streets. Not until I convince them that it's useful. So I have to go do something to convince them that it's useful first.
looks like students on the right-hand side of the main quad where they will sit and
Yeah, there's actually, because the connectivity here is pretty bad. They didn't drive here, but my guess is it's not very good around here, because around these couple buildings here, there's a lot of students living around there, but there's also businesses, so it's not clear that they actually have a university base station broadcasting there either. So, I mean, there are students everywhere, and down by the stadium, there's a little bit of connectivity, but it's not great. And now, you put a lot of people down there, it's pretty bad. So, this was all live coverage, and which was kind of cool that it worked as well. The next thing that we did was just to see how things work. We wanted to test to make sure that how connectivity worked. And I should have, you said the WINLAB network is open? WinMain is open. When I'm done, I can show you the running of this. I didn't set it up to show on my laptop. This was actually 2 cars running around, and each orange dot is where they met up with each other, essentially represented an opportunistic contact. We wanted to see how well the cars actually could do the contacts. And they drove apart for a while, and they came back together for a while, and it actually worked pretty well. In a straight line, they had pretty good connectivity. I have to get them to parse the data and tell me how far apart they were. This really was done last week, so we're just getting started on this. What else? So the key here was just testing to make sure the devices could give us that.
so the 2 cars there, they were driving.
Yeah, these 2 cars were
following each
driving
other.
around. One was following each other, and then they separated for a while. They were talking to each other on the phone, so they beat up every once in a while. They met up here for a while and passed each other, and then they met up. Okay, we're not interface people. This car is actually driving the other direction. So they passed each other, were connected for a while, and went on. So they weren't driving fast. I mean, campus speed limits only 20 miles an hour. So, the solutions that you create for the campus environment fit for people are driving faster. But this whole area actually is all about 20 to 30 mile an hour speed limits. So we don't have to deal with super fast speeds there.
What's sign fast? On the New York Thruway, you just stay in front of the tour buses and go by 2 miles.
There you go. Exactly. I mean, actually, if you're driving, one of the things that we've been looking at, and it's just something new that we're looking at, when you're driving in a cluster, you can do a lot with that cluster. Not one car has to, anybody can share information. So, highways of cars represent, an untapped resource of collaboration. So we have the OBD2 readings. We have they update their data and they can share it when there's an opportunistic contact. We can look at the hotspots to see where the most popular wireless connectivity locations, because we're tracking their location. We can add any sensors that we want. And so the goal here is to provide this real test environment. But now, what do we do with all of the data? Right? Go back to this denser environment. Because our goal is that if we have the density on campus, and we can provide solutions for the density on campus, we should be able to extend those solutions to be in more densely larger environments. I mean, in larger, just as dense environments. But we have a lot of data. What do we do with it all? And the observation that we made is that a lot of this information, almost all of this information in this particular type of application is location-based. It was sent to a particular location, and people are going to want information about that particular location. Okay. I already said this. Let me skip here a second. So we came up with a solution that's called Locus, and Locus ties, since the data is tied to the specific location where it was sensed, and not the device that sensed it. We say that data has a home location. It's this location where it was sensed. And then what we did was we just created these bubbles around the location where it was sensed. We said, okay, the data should live in this bubble. Because now, if I want to find a particular piece of data, if it actually does live in that bubble, I just need to do a geographic query to where that information is. To enable that, Locus uses DTN forwarding techniques to exchange data to keep the information in the bubble where it is and to keep the data as close to home as possible. So what happens is, if I want to access a piece of data, I can just query a geographic area. And some node, not all nodes, and not just any node, but some subset of the nodes in that area should have the data that I'm looking for. So when the query gets to the area where I'm looking, it's going to eventually find somebody who has the information that I'm looking for. Okay? But this isn't necessarily easy because I can probably get my query pretty easily to here, but what happens if this second node wants to query that data? Maybe I want to have some of the data pushed to where everybody's querying. Or maybe I want to have a deal with the accuracy. So maybe my home needs to be smaller or larger depending on the type of data I'm looking for. And all of this needs to be dynamic and needs to be based on the type of application that's running on. So, yes?
You show the arrows there as if you're querying directly the units, but the distances are too long to do that, so I assume you're going through the backhaul network.
No, I'm
But are you not going through the Wi-Fi?
So what I'm going to do is, if you assume that there's a car in front of me and a car in front of me and a car in front of me, I'm going to push it forward. And as those cars move forward and move towards the query location, they'll take it with them.
But if you have anything like the density of cars you keep showing in that toll booth picture, there's not enough spectrum around to do that.
Well, not all of the cars are necessarily going to participate in all the time. But I can certainly jump over as far as I can forward, depending on how much distance I have.
Well, if you jump over, that spectrum's still in use.
Yes, that spectrum is still in use. So this is why we need to
If
share
you're
it.
successful, does it actually work? I mean, can you afford to be successful for the amount of spectrum it takes to do that?
Can I afford to be successful?
You said not every car is going to do it, but it's going to be interesting only if a large number of people
That is true.
take advantage of it. Otherwise, you don't have an information reservoir.
I think it is. You know, I'm going to have to do more density tests, but I do believe that there'll be enough spectrum to do this. Maybe there won't. Maybe that's what research is all about. Some of the cards will carry. I mean, this is a store carry and phone. The card phone in front of you may carry it for a little while before it passes on to the next one because there wasn't enough spectrum. But if it's moving in the right direction, then it is moving towards where it needs to be. So we can use things like trajectories to help us push the data in the direction of market needs to go, push the queries in the direction.
This is the vehicular version of the 747 full of DVDs.
It is.
Moving the data around
It is.
with flash memory.
But when there is spectrum, so that's the nice thing about doing this in an TM environment is if the spectrum gets overloaded and I can't send anything, the data is not going to get dropped. It's just going to get held on to the point where I can't. And so older data either will get timed out or it'll get higher priority because it needs to get sent. I would probably make queries a higher priority so they're the things that get sent first. Because otherwise I'm never going to get my queries anywhere.
So you want really short arrows with
Yes, I do.
good information of where they're going.
Yes, I do. Short hours will come.
Flight plans, essentially.
But it means that these highways are actually moving data.
Of course, like Dan Ryan, you know what the flight plan is.
Yeah,
You sit there for a while.
Yeah, that's true. But if you're sitting there for a while, I can actually get the data forward, even though the cars aren't moving. If the cars are moving, I can probably get the data forward even faster. So a backed up highway is a very interesting network resource.
But unfortunately, that uses more spectrum because you're not moving the data by moving the cars.
It does use more spectrum, but again, we're in an environment where we're going to use what spectrum we can. And we're not going to rely on the fact that I have to have a large volume of spectrum. I'm going to make use of what I have. And if I can't send something, I'll hold on to it.
Do you have a way of coordinating the cars so that when the spectrum gets dense, they don't all try to talk at once?
We are going to do that. I don't have a solution. I don't have a solution I can talk to you about right now, but we are going to talk. We are going to look at coordinating the cars, which channels they talk about.
Tragedy of the commons.
Yeah. But the benefit is you can do a lot more. If everybody's looking, if you and I are trying to find each other, it's very difficult on a multi-channel interface. It's going to be very difficult for us to find each other. But if your group is looking for my group and we're sharing, we're actually going to find each other. So it's the same thing if we're communicating. We could probably coordinate across different channels much easier if there's lots of us.
We got a hailing channel that reduces it.
Yeah.
Possible.
So you have a question?
Yeah, so actually it's very much related. So I just want to talk about the information like that is kept on these cars and
Mhm.
things. So what if over the time a lot of information is accumulated? In that case, how do you actually prioritize all this information? How do you deal with the old information?
So certainly you're not to prioritize
Right.
information because your contacts are going to be limited. The amount of time, the amount of bandwidth that you have is going to be limited.
Right.
That's very much going to be application specific. And it's something that we're looking at to
Okay.
try to figure out, is, so certainly we've already seen that our queries have to have high priority or they're actually going to. So essentially what we're doing is saying that in this network, and I'll show you a picture of this in a second, data is going to have a high priority if it's in its home location, right? Because I want to make sure that the data in its home location is getting
So what is the-
copied.
What is the probability that the query will find the data in the home location?
That is
what if it's like behind Champagne, for example?
Well, okay, well, certainly Champaign is not going to have the density to be able to enable all of this. Right. I can tell you that the probability of it finding its home location if you don't use location-based querying is going to be very low. So I know that's the opposite of your question.
Just for this philosophy, that's also what we do here.
You're not likely to find it unless you flood. So what we're letting you do is not have to flood, but to actually geographically focus the query on a specific location.
Yeah, I just worry if the information gets really huge about each location. So how to index the information would be slightly challenging.
It's going to be,
Right.
it's going to be hard. I don't think I really answered your question.
I think they're also like old information though. You get average traffic patterns, changes in traffic patterns.
So so actually, yes, for local information, so we have two different things we need to do. Let me see if I can answer them. For data, not queries, but for data we want to store near its home location. Right. So we're going to use utility-based replication. Right. If I'm near my home, I have a high utility, and so I'm going to get replicated to the other nodes in my home.
Yeah, so they all relay.
Right. Older data is going to have less utility because I'm trying to find out most recent information. And as I get further away from my home, I'm going to have less utility. Interestingly, essentially what we're doing is we're putting an interest right here. We're saying, okay, somebody right there is probably interested in my data. You could optimize this for frequent queries. If there's somebody over here, there's this whole group of people over here querying parking spaces as they're coming off of the freeway. You could push an interest right here and have the data right here as part of its home location as an optimization. You wouldn't want it to move from there. You still want it there so other people can find it. But you could also push it here so that it's found quicker.
So predict where the information will be needed
Yeah.
and push things like that.
So you can do that as well, which will actually shorten things quite a bit and help with our spectrum problems.
That's interesting.
But the queries, but we do have to be
basing,
Yeah.
where you store you're storing all of the content based upon
where it was sensed.
where it was sensed.
Yes.
That also seems redundant from a compression data redundancy point of view, because now I have 10 nodes who are all within half a hop of each other, who all have the same thing.
Well, certainly,
So shouldn't
we've
I want to
talked
actually
about it.
separate them by at least some network?
We've looked at trying to figure out how to do this. It's not easy because none of our solutions are centralized. Right? They're all local decisions based on the network. So I could, we've talked about having replication decisions also based on the fact that if you have it already and somebody else has it already and there's enough density that it'll lose a little bit of priority. So its utility for replication will be reduced if I've seen a lot of copies of it recently. It's a very simple local solution that we can do. The other thing you can do is, if you do have a lot of nodes in a local area, you could disseminate an aggregation command. This would be application specific. You could say, okay, please aggregate your data because it's what somebody's going to ask for anyway. So you're pre-processing the query for some specific kind of data instead of keeping all the old data.
Another idea would be if you've got many nodes that kind of know each other's existence and they're all localized around this darker blue circle,
Yeah.
then they should also coordinate their own resources. Otherwise, one of them might end up filling up its hard drive or whatever, and another one's.
So when you have cars moving, right, our energy resources aren't an issue, but maybe our storage. But Storage is going to come and go because I'm going to be moving through different areas, getting the data from one area, and then I'm going to get the data from the next area. So there's quite a bit of churn on the data. But if I happen to have a couple of parked cars in that area, they should certainly coordinate themselves. And this is, this leads to the comment that if you have connectivity, take advantage of it, and then let them coordinate and optimize for that. But you can't plan on that. You have to have a solution that doesn't assume that that's going to be. But you do have to have a solution that can take advantage of it. So this is exactly what I just said. If you notice in the home area, you want to copy it with a higher priority. The queries, on the other hand, if I just use, existing DTN forwarding just tries to connect to users, but I'm not trying to get to the user, I'm trying to get to a location. If I use the same type of utility-based, location-based utility for my replication, my query is very far away, it's going to have a very low utility. So I need to push the queries in a separate priority class than the data, and probably make multiple copies of the queries to ensure that each other. So what we started to do was seed the queries using a quota. So each query had maybe 10 copies and sent them out through the network. And if it was forwarded with a very high utility, if the distance from the peer, the distance to the peer right now is greater than the distance of the node that's so the distance of my peer to the home location is less than the distance of what my current node is. So if you're closer, you get to forward. What?
Is your query a geographic query? Or
yes, it's query is a geographic.
It has attributes like.
Yes.
Do you query based on multiple attributes,
We have to.
including geographic or
So
just geographic? Because that it looks like you're using some kind of a content routing scheme here.
yes,
But the packet, does it have a header which maintains a content,
Certainly.
dedicated content?
it's going to have. So is it going to have something along the lines of? This is why we might want to start aggregating some of the data anyway. If somebody says, how many parking spots are around this intersection, I don't want to have to get answers about all the parking spots. I want that data aggregated.
Yeah, because many of your queries may not have a specific geographic target. Like we can open it, like where is the content? So
That's a little harder to do.
It's
If
harder.
I'm going to say where is, that's a much different thing. If I wanted to disseminate information about where we're looking at the other way around, looking for information about a specific area. I know I'm going this way. Is there congestion? So I'm assuming that if I have 3 choices or 4 choices of directions I can go in, I can query those 4 routes, and figure out which ones have the most congestion. But if I don't want to have to say, if there's 40 routes, for me to query all those is probably overkill for this technique. And essentially any node, I said this before, any node in that location can provide a response. So we did look at this in a simulation because obviously we couldn't quite put it out in the real world yet. And the things that we wanted to understand is what different type of policy. Now, obviously, we didn't have another location-based querying to compare to, but we wanted to answer the question, exactly the question that you asked before, what happens, how frequently do we find it? So we had 150 cars in the map of Chicago, so it was actually using the map of Chicago in a 25-kilometer square area. So not too dense, but not too bad either. A fixed bubble size of 500 meters. And just data bytes that were 1 kilobyte. And some queries were sent every 5 seconds through the network. So the first thing we wanted to look at was that did Locust keep the data near its home? So what we've got here is over time, data was sensed. And so of course, in the beginning, the data is going to be where it's sensed because that's where it is. But as the nodes move around, the data is going to get further and further away from where it was sensed. And this red line, I'm not sure why they're dotted, they're just moving that way, is the location-based. It's Locust. So Locust keeps the data much closer to its home than anything else.
So what is the unit and the x-axis?
This is just time. So over time,
That's seconds, minutes, or?
seconds, I think.
Oh, I see. So
Yeah,
this
it's a
is
second.
within a short time frame.
This is within a short time frame.
I see.
But what's interesting is that I'm pretty sure when we ran it longer, we just kept, you've got a limit, since we have a limit on the size of the network, that these are not going to get that much further away. It was only 2,500 square feet per year. So you can't be that far. But we were definitely able to keep the data closer to its home location, which is what our goal was.
And that actually could have been made, the way we ran those simulations were, that red line could have been dropped smaller, but the buffer
The buffer
size,
size was large.
it was 800 if you saw on the previous slide,
Yeah.
there was a 500 plus a 300 buffer, and so you could shrink that depending on the size of the buffers.
But if you shrink it too small and your density is not high enough, you're not going to be able to keep anything here. So our
Explaining that for
things just got dumped when they. So we kept everything as long as we had buffer space for it. Nothing expired. So if there was enough buffer space, everything could have been kept forever. But there wasn't enough buffer space, and it was the oldest stuff out first. So the second question was, what was the number of unique messages in the system? Because it would be interesting to say, okay, this is an odd metric, but it's interesting. This is the number of unique pieces of data. And you'd think that you'd want to have more unique data in the network so that I could find it. So if we look here, this is also time over here, and this is the number of unique messages. The location, which is the red one, didn't do a great job of keeping unique messages in the system. The least sent, which meant that it hadn't been sent as much as everything else, did the best job. But if you can't find it, it might as well not be there. So the approaches that kept more data in the network would have required flooding to be able to find them. And they wouldn't be able to be found if we used this geographic approach. So just a, again, quick evaluation of it to look at the query success. This is obviously we do better than that, but we had to, right? Because we kept the data near its home location, and it gave us the ability to improve the query success rate from about 10 to 15% for the other types of approaches, all the way up to over 35% success rate. Now, in a DTN, your success rate is never going to be 100% or something. So really keeping the data near the home location increased the query success rate, and the location-based forwarding increased the response to success rate. One of the interesting things we looked at was just trying to understand what about for old data? What if we had older queries? And again, we were focusing on trying to find the most recent information. And the best improvement is for the queries that were more recent. So this is queries that were within the first 0 to 12 seconds, 13 to 24 seconds, and so on. And so if you look at the most recent queries, you see that the location-based approaches really do well. And as the queries get older, the data is going to disappear. We're not going to do very well at all. But that was our goal. That was the intention of the approach. So the fewer unique messages essentially was leading to lower historical query success. So our older queries are getting bumped out. So given all of this, we had a couple more questions. This is not finished, but things like where should the data live? Should it live where it's sensed or where it's needed? This was that idea that we could move an interest to where people are actually asking about the data. What about accuracy and proximity? If I make my bubble too big, my accuracy is not going to be very good, but I might be able to get more information. And we also need to understand how to expedite queries and to manage accuracy and response time. So things still need to be improved. That is the last part of that particular piece. If anybody's questions.